Okay, so in this part of the course, we will talk about routing, and I will show you, say, fundamentals of routing, uh, mainly focusing on the routing algorithm. Uh, we will not have time to go through the routing protocols, so I will ask you to study a condensed version of the original slide set on the protocols by yourself because they are quite simple. But instead, algorithms are more difficult to understand, so I would like to present them to uh, here in class. So we are just going back to the general IP layer 3 features in order to understand what is better understand what is routing, and then we are going to introduce the algorithms that are mostly used for this purpose in their say, centralized formulation and also in their distributed formulation. So what is routing? Here we are focusing only on the unicast routing. Multicast routing is out of the scope of this course, but it exists anywhere. Anyway, so it is the basis of layer 3 functionality. As you know, in layer 3, the network must be able to carry packets from a source to destination through a set of hops or a set of nodes. And when the source and the destination are not directly connected. So we are talking about connectivity at the layer 3. It means that each of these links that you see corresponds to a layer 2 network, but each layer 2 networks are isolated one each other and they are connected by the routers. So if A and B are not on the same layer 2 network, you need to find a path across the network, across the set of hops. So the layer 3 entities have to select what is the output port to use for a specific for each specific packet that is coming to a specific input port. And to do this, they must use a routing table, as we have just seen. But this part is not on forwarding. So what happens basically as a mechanism inside the router in order to manage a single packet, but it's more dedicated to how to find the paths across the network. No. So this is the output of these functions, that is routing, is a path across the network that takes packets from a source to a destination. In order to find the path through the network, we have to look at the topology of the network. In some cases, the topology is very simple, as in the exercise we have seen. Each source and destination are connected by a single path, so you don't have any choice. But in the general case, the network is much more connected, and so we must be able not only to find a path, but also to find that path that, according to our routing policy, is the best one. Okay? And the routing policy must be there in order to select between different possibilities, different paths. And it usually corresponds to a routing algorithm, so a mathematical formulation of the problem that allows you to find a specific path among different alternatives. Then once this path is found, it is translated in the single routing tables, entries of the routing tables of all the routers that are crossed by the path, so that each router can then perform its forwarding function, which is looking at the table and send the path to a specific output. This is different according to the fact that we are considering datagram service or virtual circuit service. We have already introduced the virtual circuit service. Basically, the big difference is that in a virtual circuit, you identify a packet as belonging to a specific flow. And so not only the output is interesting, but also which input port was used by the packet to arrive to the node. In case of datagram, you are just identifying the destination of the packet. So the routing algorithm determines the end-to-end path calculation that is then used to create or to write the entries into local forwarding tables. And then once the local forwarding tables have a specific entry, the forwarding mechanism takes place in each node that is crossed by the packet. The routing protocols are the mechanism by which we can perform in a network a routing algorithm. And so in order to perform a routing algorithm, we have to overcome the single environment of a single link, because here we are talking about an end-to-end path. So in some way, we have to know the topology of the network, and usually this is done by the router themselves by exchanging information of reachability, information of the connection between the different routers. And so this is a way to learn the topology, and then also the router communicates so that the best path is selected by the plurality of the routers in a consistent way. So each router makes its own action in the routing mechanism, but at the end you have an end-to-end consistent path. The protocols describe the exchange of messages between the routers in order to support the routing function and the routing algorithm. And so the protocol tells which kind of packet are exchanged, what is the frequency of exchanging, and how the routers have to react to the modification of the topology or arrival of new packets, and so on. This is all defined by that protocol. When you have so why we need this routing calculation? As I said, when you have a broadcast network that is performs always the broadcast of a packet to all the stations that are attached to the network, you actually don't need any routing function, because you're sure that the packet will always be delivered to the final destination. But in this case, the maximum traffic that can be transferred to the network is constrained by the capacity of the channel, the broadcast channel. No? For example, if you have a radio transmission, where each time you send a packet by radio, all the stations that are connected to the radio will receive the packet. But if you don't have means to let's say, share this capacity between different packets with suitable access control, each time two stations are transmitting at the same time, all the other stations will not receive anything that is identifiable, will receive just noise. Okay? So in this case, when you have a perfectly broadcast channel, the only way is that the channel can be occupied by a single transmission at a time. So the throughput of the quantity of information that you can send through the network is limited by the channel capacity. When instead you have a mesh network, you have several possibilities or several paths connecting the source and the destination, and therefore you can exploit parallelism because you can send one information on a path, along a path, while you are sending other information on a different path. They will travel in a difference of space difference, so they will never meet, and therefore you can use the capacity of more than one channel in parallel. So in a mesh network, you are increasing the capability of the network of transferring information, the throughput, so-called. But you need a routing policy, because you have to decide between different possibilities. And if you take the wrong decisions, then you may not be able to exploit all the possibilities of the network. For example, here you have this set of the two sources and two destinations from one side and the other, and the routing decision has been taken in a way that all the traffic between the sources and the destinations will go through the same set of links. Okay, this means that you don't have the possibility of increasing the capacity. You are again constrained by the capacity of the single link. So they need C. If C is the capacity of a single link, then you cannot transfer more than C information by second through this network. But this is because the routing decision was not taken in an optimal way. If you change routing, for example, you apply a routing algorithm that takes into account the fact that the path is already busy, and finds another path in case the path is busy, then you can exploit the meshed nature of this network, the mesh topology, in order to increase the capacity. So in this case, the maximum throughput will be 3 times C, because here you have again the sharing of the same link by two different flows. But in this case, you cannot do anything else because you have a single physical link that is connecting this node to the rest of the network. But still is an enhancement compared to the previous case. So in internet, we are applying all these concepts basically on the IP layer, so layer 3 of internet. And this means that we are applying routing in a network environment that is providing only the datagram protocol, the datagram service. So we know already that in the IP protocol, forwarding is based on two aspects. First is the destination address, so it's a destination-based forwarding. The second aspect is next hop routing. So each time a packet arrives into a node, the node only knows what is the next stop in terms of forwarding function, what is the next stop where to deliver the packet. As a consequence of this way of implementing forwarding, we have also a specific condition on routing. Okay? And more precisely, we know that packets that are addressed to the same destination and that are coming to a certain routers, that is in between inter, will always follow the same path because they will be routed to the same next hop router, regardless of what is the input link. Okay, so these two packets that are arriving to R from different input links and however have the same destination, which is D, they will be forwarded on the same next hop router, towards the same next hop router. This is a feature that constrains the routing decision in internet. So we must take into account this when we are establishing the routing decision. This is not true, for example, in the case of circuit switching, because even if these two packets are forwarded to the same destination, but they belong to different circuits, so they have different virtual circuit identifiers. In principle, they can be routed on different paths. Okay? So this router here, if it's a circuit switch, virtual circuit switch, will be able to send the packets on different paths. But if it is an IP router, a simple IP router, this is not true. So we have this constraint, and this means that when we are finding the paths in IP, the set of paths from each source is going the same destination is actually always a tree. Okay? And so you will have trees of minimum cost paths, as we will mention later on. So now here you can see that if we are going to D, that is this destination, and we are reaching this destination from different sources like S5, S1, S2, and so on and so forth. If you put together all the paths that can be found in order to arrive to D, the result is a tree. Has a tree topology. You cannot route independently each traffic flow. So IP routing is based on a simple principle that is the way to select the path. Always choose the shortest path to the destination. But the trick is, what do we mean by shortest? Because we have to select the shortest path, but the metrics that we can use to measure if a path is longer than another one can be different. Okay, the metric is general. We can use various physical parameters, as we will introduce later on, to compare the different paths. The calculation is always done in a distributed manner, so there is no single centralized entity in the current use of IP, which is deciding for all the routes, but all the routers cooperate, exchanging information with each other in order to perform, to take the routing decisions. And so you must also guarantee that these routing decisions are consistent. And there is since we have this tree structure of the paths that are going to a certain destination, coming from all the sources, we have also a property that tells that a subpath of a minimal path. So if once we have found the shortest path, for example, from S3 to D, then a subpath of this shortest path is also the best path from an intermediate source to the destination. So, for example, if I want to go to D from this node, this is the best path. If I want to go to D from the previous node, the path from this node to D contains the path from this node to D. Okay. And then we can go further on until we reach the longest path in this tree. Okay. So once we find that the path from S3, the best path from S3 to D contains S5, we also know the path from S5 to D, because the path from S5 to D will be a subpath of the path from S3 to D. Okay? And actually, we also know that the best path from S3 to S5 is the same. Is a subpath of the path from S3 to D. What are the features of the routing algorithm that we can use in order to take these decisions? First of all, we have some requirements which can tell us what is a good routing algorithm for to be applied on the IP network. The algorithm can be simple, have to be simple because it will be executed by all the nodes, so you cannot do something very computational intensive, otherwise the reaction time will be too much. It must be robust. This means that if you have a change in the topology, the algorithm should be able to automatically adapt to this change. It should be stable, so if you have a change in the topology, the reaction to this change should not cause the paths to oscillate. Otherwise, this is not very pleasant, because you have continuously to update the routing table that way. And also, it should be optimal in some according to some metric. Another feature that distinguishes between different algorithms is where the routing decision is taken. So we have the distributed algorithm that we have those that I have talked so far, and those that are applied to applicable to IP. But there is also the possibility of having centralized algorithm where there is a single control center that makes all the decisions, and even isolated algorithms. So these algorithms are such that a single node is able to take all the routing decisions, at least for a certain portion of the path, or for all the path from the source to the destination. I will skip this classification. Unfortunately, I didn't translate it in English, but I think you can easily understand also the Italian. I leave it to you. There are several possibilities, but the right cases are those that are applicable to IP. And we are talking with IP of a routing algorithm with the table. So routing algorithms that also that are based on the use of the table, and also leave this to you to go into the details. The case, the centralized case is possible, and in the IP network, it corresponds to the fact that the routers, the routing tables of the IP routers are filled in manually by a network a network administrator, maybe also remotely, but in any case manually. And it is when you do this, of course, you have drawbacks. First of all, because each time you have a change in the topology, then these routing tables must be reconfigured. While if you don't have this centralized manual control, the other algorithms are able to adapt to changes of the topology in a dynamic way. However, you can be more effective because you have the vision of the whole network, and then you can, for example, apply some network planning, more accurate network planning strategies called traffic engineering. This is in the old times, this was all manual. So when the centralized control of the routing tables was manual, recently this is the base of the software-defined networking paradigm, where you have a controller which is doing the same that was done before by the network administrator, but on the basis of a software. So it's also able to do it automatically, dynamically, potentially dynamically. And the more very important, the administrator doesn't have to configure all the routers in the network because this is done in a central way. However, we are not covering SDN. If you're interested, there are other courses, for example, switching and routing, which is a course that I'm teaching in parallel of this. The project will be using SDN, if you're interested, maybe next year. So now we are talking about dynamic routing, which is performed by the pool of the routers in the network operating on the basis of a routing protocol. So the routing protocol, as we have mentioned, defines all the elements of this strategy. That includes also the metric that is used to evaluate the cost in order to find the best path, comparing different paths. The algorithm that is used to choose the best routes in the minimum cost. How update messages are exchanged, type, content, and frequency, and so at the end, the router that is the routing function that is performed is dynamic. it's able to adapt automatically to changes in the network topology. What is the advantage of having a dynamic routing function? In this way, you can change the routing tables whenever you have a change in the topology. And for example, you may be able to react to changes in the topology on the physical layer of the two when you switch on or switch off a network or a link, but also changes in, for example, the state of the network. Maybe you have a congestion as a specific link. This means that the link gets overcrowded by packets. If you are able to detect this event and translate it into a failure at the layer 2, then automatically the network at layer 3 will react to this event. And of course, it will react also to failures. This is an example. Imagine that you have a certain destination, and here is the source, this side, and here is the destination. You have a certain path that is being calculated in the time where the network topology was stable. And then there is a failure in some network elements, for example, in a router. Clearly, this failure cannot be detected, for example, by a router that is here, because this router has no direct access to the failure situation that is remote. Maybe this router is able to detect a local failure, and in fact, this is a very special, particular aspect, but you should know that routing tables sometimes can have double entries where you define next hop information that is in the normal conditions and a backup next hop information in case the link on the output interface that is going to the next hop is in failure. But this is only a local mechanism, so you can, in this way, you can resist to local failures. In this case, the failure is remote. So the only way to adapt this change is by using the routing protocols. When you have a failure here, the neighbor routers will detect the failure, and by sending information out with the routing protocol, sooner or later this information will propagate through the network. And then, once this information is propagated, each router changes its own routing table, so you can create automatically a new path to the destination. Okay? This new path is out of the failure, so it's basically fixing, reacting to the failure. So usually, each protocol has an algorithm that is able to find the best route, and in the most general conditions, the routing problem, finding the minimum path, is a problem of polynomial complexity. This means that it is basically simple. You can solve it in a reasonable time, and using dynamic algorithm, you can have a response in a reasonable time. If you take instead the general optimization of all the paths in the network, this is going to be an NP-hard problem, or NP problem. So if you have a centralized router, a centralized controller, and you want to optimize all the paths, then it will take a lot of time. But in case of a distributed algorithm, since you are optimizing a single path at a time, this is a polynomial problem. Okay? So you can then read the story of the salesman. Okay, I think that I have to stop now. So tomorrow we will go through the algorithm and hopefully we will be able to finish this part on routing algorithm, and then we will see the next lessons. Okay.